Okay. Welcome everybody to this week's GBO Community Zoom. I'm Jim Jackson. I'm the director here. Jay Lockman can't join us today, so I'll be taking over his hosting duties. Just a quick thanks to everyone who sent in a proposal to the Green Bank telescope. We got about 61 proposals, which is about typical for us. So thank you for those of you who submitted proposals, and you will hear from us in due course. Business as usual at the observatory. We're in action, and all is well, collecting lots of good data for the community. Today we're going to have a talk by Eric Koch. He's a postdoc at the SMA at the CfA, and he's going to be talking to us today about the kinematics of the atomic medium in galaxies. So Eric, please take it away.
All right, thank you, Jim. Just let me share my screen and set up the slides. All right. So thanks for the invitation to speak today, and thank you all for joining. I'm excited to share some of our recent results looking at the detailed atomic ISM kinematics across our local group galaxies that we've produced by combining GBT and VLA observations of the 21 centimeter H1 line. And I'll talk a little bit more about the end of a now ongoing VLA Extra-Large program that's expanding our sample significantly from what I'll show today. So I'll specifically show mostly our results with respect to M33. This is the map that you see here on the title slide. And I'll especially highlight the crucial role that short spacing provides for tracing the entire structure from a large galactic scale down to the small scale of giant molecular clouds. And yes, the crucial role of the short spacing provided by the GBT and some of the results that follow from that. So this idea of the atomic ISM being a great tracer of galactic and small scale structure really provides the large background for why we care so much about the atomic ISM. And so this this beautiful video created by the TNG collaboration is demonstrating how the evolution of a galaxy is intrinsically coupled to its surrounding environment. And if we want to understand that in the context of galaxy evolution, we need to be connecting these sort of large scale, what's happening in the surrounding environment around a galaxy, down to the small scale processes within the disk like star formation to piece this whole story together. In particular, this video does a great job of showing the ongoing accretion process of gas throughout time and the outflows being produced by different feedback processes as well. So with that in mind, very broadly, our goals here are to try to start to connect larger scales beyond the immediate environment of a star-forming disk down to the properties of the disk itself, and connecting that to the baryon cycle as what's going on near the midplane of the galaxy. And so that's the transition from the atomic gas to the molecular, the subsequent star formation, and then the feedback, the energy and momentum provided by the massive stars that create this loop, driving gas back outside of the galaxy and the connecting piece of the gas continuing to accrete. One of the crucial roles of the atomic ISM here, sort of gluing these things together, is that it's the dominant, by mass, is the dominant component of the neutral ISM in the present day, the nearby galaxy population. And so one role these observations can play is to start connecting some of the open questions about how these scales relate to each other, to try to put together a comprehensive understanding of the baryon cycle and its relation to galaxy evolution. And so with that in mind, the local group galaxy is a fantastic laboratory to be starting to explore connecting large to small scales for sort of individual galaxy studies. And we can roughly think about this in terms of what we have from current radio interferometers for where we have sufficient surface brightness sensitivity to be mapping this extended H1 structure. So with the VLA, that's about 6 arc-in-second scales. Going a bit beyond that, we really lose out to the surface brightness sensitivity. But since the VLA's upgrade, the correlator has this fantastic amount of flexibility that we can, compared to previous studies, look at much finer spectral resolution over the entirety of some of these larger galaxies that are so nearby to us. So the image I'm showing here, we're looking at about 100 parsec scales. And this is combining the VLA and its C configuration with GBT data. This is the inner part of J's much larger map of the M33 and its surrounding environment. And so to give us an idea of what the structure looks like in this galaxy, I've created this 3D render. So I've tipped the galaxy, so the velocity is now along the y-axis. And you can see what's really being highlighted here is M33's rotation curve and the structure of the bright H1. So in comparison to previous observations as either very well studied targets, we're reaching a much finer spectral resolution of about 200 meters per second, but still with fantastic sensitivity. And so roughly speaking, this would allow us to resolve components from the thermal line width of cold atomic gas, so temperatures down to about 100 Kelvin or so. I'm mostly going to focus on the small scale structure there, but that's one of the reasons why we're motivating why we need that really fine spectral resolution. So this mostly showed us the bright structure. We can look again, creating the same sort of 3D render, but this time I'm going to change the contrast so that we can see the abundance of structure far closer to the noise level. And when I do this, you can see that there's a number of these off-rotation velocity components. There's discrete structures. As this structure comes around, you'll be able to see these fine sort of velocity features, sort of hair-like structure that we find throughout the galaxy. And so what this is suggesting is, despite having a fine spatial and spectral resolution, we have enough sensitivity to go just beyond that star-forming disk in probing the H1 and its connection to the larger scale structure and M33's halo and warp disk components. And so these 3D renders are very nice, but to get a sense of what are we looking at in terms of individual spectra, I've pulled out 4 different examples here. These are individual spectra taken from the data cube that we were just looking at. And qualitatively, what I want to point out is that we're now starting to see hints of the spectral complexity that we're more used to seeing within the Milky Way, where of course we're looking through the disk and there are many components along the line of sight, or the Magellanic Clouds, so things that are much nearer to us. So we see multiple velocity components of different shapes, and we also see these low surface brightness, very extended velocity features, these sort of line wing structures that occur throughout the disk. And so the results I'll be showing today really focus down into what these line wing structures are, where they're coming from, and how do we start to interpret them, and in particular, how they start to break down the assumptions that we use for basic measures of H1 kinematics in extragalactic data. So here I'm showing 2 representative spectra again, but now I've split them apart into 2 different things. So the black curves are the VLA plus the GBT, so that's short spacing corrected. And that was the spectra that we were looking at before, was that combination. And in gray, I'm showing what these same spectra look like with only the VLA component, so not short spacing corrected. And what you can see is that while the peak structure looks fairly similar, it's the GBT that's providing these extended line wings. So they're mostly coming from the short spacing component. The other thing that we noticed just by visually looking at this data is that these line wings tend not to be symmetric about the bright structure. And in fact, most of them are asymmetric. One way to quantify that asymmetry about the line is to calculate the skewness parameter of these spectra. And we can do that for every spectrum, and we get a map of skewness that looks like this, where we see 2 distinct halves of the galaxy. M33's north is its blue shifted limb. And we find that the asymmetry of these lines is preferentially redshifted, and vice versa for the southern redshifted limb of M33. And so in both cases, this is corresponding to more emission closer to M33's systemic velocity. So in the northern half, we have this redshifted tail closer to the systemic velocity. In the southern part, we have a blue shifted tail. And so what this is indicative of is rotationally lagging H1. So this would be H1 coming from farther heights or larger heights away from the midplane. So if the midplane is moving at a circular rotation velocity, as we move farther away from that midplane, the gas feels less of that gravity, and so it tends to rotationally lag. So this large scale structure in these extended line wings is tracing what is likely a thick H1 disk that's rotationally lagging compared to the midplane. And again, to really highlight, we can look to really highlight the importance of the short spacing here. We can calculate the skewness without the GBT component and compare that to the map that we see here. And so that's what I'm showing in this new plot. And what you see in the VLA only on the left-hand side is that we've lost a lot of that large scale structure. We still see a little bit of it, but mostly we're seeing variations on a much smaller scale. Those variations are probably interesting in their own right, probably localized events. But to create this sort of larger scale picture of what does this galaxy look like in its connection to its surrounding environment, we really need that short spacing correction to place it in its full context. So we have this sort of thick component, and the H1 spectra are a little bit more complex than what we often see in extragalactic H1 studies. Another place where this begins to affect our measurements is in moment analysis to make simple estimates of the H1 kinematics. And so in this part of my talk, I'll show a couple examples of how these asymmetric extended line wings impact measures of the centroid and from the line width as measured by the second moment. So starting with the centroid, if we look sort of just with a representative spectrum, the centroid is just a weighted mean over the entire spectrum. So when we don't have this extended line wing component, which in this case is for the VLA only, the centroid velocity ends up being quite near to the peak temperature, or the velocity where the peak temperature is located at. But because of this extended line wing in the combined data, that centroid ends up being pulled over due to that asymmetric feature. And so we can also map what is the difference between these two centroids with and without short spacing. And we end up with a map that looks very similar to the skewness that we saw before, that the centroid is preferentially redshifted in the north and blue shifted in the south due to these asymmetric line wings. So the colors here is going from about plus or minus 20 kilometers per second. For reference, M33's maximum circular rotation velocity is a little over 100 kilometers per second. So in localized regions, it can be a fairly significant difference. And so with that in mind, we can use we can compare different measures of the line center, the centroid, or other properties to see how that would impact the rotation curve that we measure for M33. So I'm showing 4 different rotation curves as measured using the DiskFit software, where we've given different input data to define what the line center is. So 2 of them are the solid lines are the centroids, which we were looking at before. And the dotted lines are using the velocity at peak temperature. So just wherever the peak of the spectrum is located. On the left, we have the actual fits to radial bins. It's maybe a little bit more helpful to look at the smooth parameterization on the right. And we can see that there are 3 that are roughly on top of each other and hard to distinguish. But this red solid line ends up being significantly lower. And that's the centroid from the combined VLA plus GBT that was affected by those asymmetric line wings. So it's a fairly mild effect. The maximum rotation velocity from this fit is about 10% lower. And it's not particularly significant. It's a difference of a little over 1 sigma for individual bins. But what it's suggestive of is that some of the approximations that have been made along the way don't accurately represent the complexity of the data that we're looking at, and using a more complex rotation model is probably warranted for the data quality that we have. The other property that's significantly affected is this measure of the line width coming from the second moment. So here the line width would be the square root of this equation here. And so we can again look at this spectrum as an example of how these asymmetric line wings end up affecting this measure. So for the VLA only, we get a line width that would be sort of roughly corresponding to this shaded area that I'm showing here. And in the presence of the line wing, it gets inflated by about 50%. So if we were to look by eye, it would be giving us an effective width much larger than the bright sort of component that your eye sort of locks onto around this velocity. And so we compared across the galaxy, what are the line widths that we get with and without the GBT component? And we get a difference that's fairly uniform across the galaxy. So this is the H1 line width on the y-axis plotted against the galactocentric radius. And each measurement here is an average of that line width in radial bins. So there's about a 50% difference between having the GBT versus not having the GBT component added in. So for reference, typical extragalactic H1 line widths are around 10 to 12 kilometers per second. And the thing that we often compare this to is an approximation for the thermal line width of the H1. So assuming that the volume filling warm component is dominating the emission, the thermal line width corresponds to about 6 kilometers per second. The excess is typically attributed to turbulence. So in this example, we have this sort of thick rotationally lagging disk that would end up producing larger line widths from this given method. And so we infer a larger amount of turbulent energy needed in the medium. The same difference occurs when we use different definitions of the line width itself. So now I'm just showing the same line width versus radius plot measured in different ways using only the VLA plus GBT data. So the second moment that we looked at before is this solid line towards the top. And the three other measures that we see are estimated from line stacking. So this is taking a definition of a line center, shifting all the spectra in a defined region, in this case radial bins, to that same line center, and then co-adding them and estimating the width from that stacked spectrum. And the difference between these three is just different definitions of what the line center is. So these green diamonds are from stacking against the circular rotation curve. The red circles are from the centroid, and the narrowest ones, these purple triangles, are from stacking at the velocity at that peak temperature. What's interesting is, again, if we're taking that in excess of the 6 kilometers per second as the turbulent component, this large range of over 50% from these different methods causes a large range in what we'd infer for the energy dissipation rate due to turbulence. So this plot is showing that range. So the range of line widths that we have is this shaded gray area. And I'm comparing that to the expected energy injection rates from different mechanisms, supernovae in the solid line and MRI in the dashed line. And you can see that our measurements are roughly consistent with supernovae, with the energy injection from supernovae, which is consistent with most other surveys. But the thing to highlight here is the large scatter that we're seeing is due to differences in the methodology of how we've measured the line width and not a statistical uncertainty. So providing more detailed comparisons to turbulent driving in the ISM really requires more sophisticated measures of the kinematics. And so with this in mind, we're starting to explore these directions with some of the new data that we have. So incorporating a more sophisticated rotation model that treats the galaxy as a three-dimensional structure and uses the entire spectral line data cube. And on the right, I just have a few examples from one of my recent papers where we start to explore more sophisticated kinematic modeling for individual spectra. And so this is going to be important for what is now an ongoing extra-large program, the local group L-band survey, or LGLBS, supported by a very large team. And so we're about 1 year into the start of our observations and have another couple years to go. So hopefully you'll start to hear news from us in the next year and certainly the years to come. And so this program will expand significantly on some of the work that I showed today. So from M33 to the entirety of M31 and the 4 northern star-forming dwarf galaxies that are accessible to the VLA. So this will be expanding on some of the observations that I showed today. So high sensitivity at about 100 parsecs, pushing down to sort of tens of parsec scales to map in the H1, what is the structure of the H1 on giant molecular cloud scales. And then due to the VLA's fantastic flexibility in its correlator, we also get the full 1 to 2 gigahertz polarized continuum. And that's the place where we can really take advantage of the long baselines from the VLA to produce deep arc-second radio continuum maps tracing supernova remnants and H2 regions across all of these local group galaxies. So we're still actively observing, but we've put together quite a bit of our data for tracing these local group star-forming dwarfs on sort of 100 parsec scales, roughly equivalent to the M33 data that I was showing today. And though we only have 4 of these galaxies, you can see just across this local sample, there's a diverse range in the H1 structures that we're seeing in these dwarf galaxies. So this will be interesting to explore with these data over the coming year. And so with that, I'll just leave you with my conclusions today. I hope I demonstrated the importance of short spacing in some of these H1 studies for nearby galaxies. In particular for M33, the short spacing from the GBT is essential to gaining this sort of full perspective of the galaxy and the H1 in the surrounding thick, rotationally lagging atomic gas disk. At the same time, our spectra are getting quite complex. And so this requires improvements in the ways that we measure the H1 kinematics. And as part of the local group L-band survey, we'll be exploring more of these complex methods that are applicable to these data, but will certainly be applicable to the next generation of radio interferometers as well. So thank you very much for listening. I'd be happy to take questions.
Great, thank you for that really nice talk, Eric. So please enter your questions on the Q&A line. I see a couple of them coming in. So the first is to quantify and or correct your mean velocities and velocity dispersions to account for the low velocity tails. Instead of using, for example, the velocity at the peak temperature as you have done, have you tried using instead a Gauss-Hermite fit mean velocity with skewness kurtosis, as is routinely done for stellar kinematics? If so, interesting results.
We have, for the most part, there wasn't much of a difference compared to using just the peak temperatures in that case.
Okay. Second question, could you comment a bit more on how you define things like line width for the more complex spectra you've shown?
Right, so I think that's, that maybe doesn't have a necessarily simple answer. If I go back to the examples that I showed very briefly at the end, I think there's multiple ways you could go about doing this, and it probably depends on the science question that you want to ask. So what we found in this particular paper is we compared 2 different models, one making opacity correction, these are the fits on the right-hand side, and we compared that to a multi-component Gaussian decomposition on the left. And we largely find, these examples are very clear, but what we largely find is the multiple components tend to be preferred. So this is arguing that that perhaps the line widths should be interpreted on a per component basis if you're looking at much smaller scale structure, and depending on the galactic structure as well. This top one is Andromeda, which is highly inclined, and we're likely seeing multiple components along the line of sight. So I think it requires a lot more dissecting and will probably vary depending on what your particular science school is.
Okay. I'm going to take my prerogative and ask a couple questions. So the first is, so when you showed the kind of the velocity field view, and you had these long kind of high velocity threads or hairs, I think you called them, are those associated with star forming regions? Is that what's stirring up the gases? Are we looking at chimneys, or what are those things?
This is, yeah, that's a fantastic question. I think it's a little bit unclear from looking at the data by eye. So there's a couple general properties. I don't have an example in this set of slides, but if we go past a really bright star forming region, for example, NGC 604 is this giant H2 region in M33, you do see hints of the line wings on both sides increasing and then going back down as you go over that area. So certainly part of it is going to be due to feedback from star formation, but there also seems to be quite a bit in the outer regions of the galaxy where there's not obviously much star formation going on. And those new data of the dwarfs tends to show something similar as well. So this could be accretion onto the disk. It could be otherwise unresolved, not quite high velocity clouds, but maybe low velocity clouds. And I suspect it's probably a combination of all of the above.
Fascinating. All right, I have one more question too. So the difference in like line width between GBT plus VLA and VLA only is suggesting to me that the more diffuse gas or the more extended gas is more turbulent. Is that the correct interpretation? And what's the physical explanation for why that might be?
Line widths do tend to get a little bit larger. I think I'm not sure if it was necessarily connected to turbulence. I think we are seeing a lot more of the actual three-dimensional structure of the galaxy.
So you're probing.
So I think a lot of that
more velocity space, right? That
would be
seeing more material.
That would be my interpretation. And that asymmetric component that's probably coming from the lagging disk is about a third of the flux in those line wings. So there's room for other things, but I think as a whole, the 50% increase I think is mostly being driven by seeing more of the H1 volume.
Okay. And does this have any bearing on the mass estimates of either the gaseous component or the galaxy as a whole for your results?
So we did a comparison. It's not that significant of a difference. And if we compare it to, I guess, the various single dish observations, the masses that we get are roughly consistent with the field of view that we have. The asymmetric component is about 8% of the total flux, and that is about 80 million solar masses. So it's a fairly small component compared to the galaxy as a whole, but not negligible.
Okay, great. If you have more questions, please put them in the Q&A chat. All right, seeing none, I'm just reminding everyone of the upcoming GBT training workshops in the next couple of weeks. So I've put a link in there. And Eric, thank you for a very interesting and well-presented talk.
Thank you very much for having me. Thank you, everyone.